I'm David Stork, and I'm going to be talking about computational symbolic mathematics, a course I teach at Stanford University. I first like to thank everyone at Wolfram Research, and especially for the Innovators Award that I received the other day. Let me start with this quote from Ada Lovelace. Many persons who are not conversant with mathematical studies imagine that because the business of Babbage's analytical engine, the first real computer, is to give its results in numerical notation, the nature of its processes must consequently be arithmetical and numerical rather than algebraic and analytical. This is an error. The engine can arrange and combine its numerical quantities exactly as if they were letters or any other general symbols. And in fact, it might bring out its results in algebraic notation or provisions made accordingly. This from the first half of the 19th century. And one of our most famous late mathematicians, John Conway, wrote, "I use numbers reluctantly." Well, that's what I'm going to be talking about. I teach a course in ICME, the Institute for Computational Mathematics and Engineering, and here's a list of representative courses offered by ICME: vector calculus, ordinary differential equations, probability and statistics, machine learning, and so forth. And the unifying thread in all of these courses, really all of them in the entire ICME before I got there, was that the computing was numerical, that you were dealing with numbers. But much of science and mathematics, of course, involves equations that do not admit numerical solutions. And we're going to see many of them. And that's what my course is all about. Using computers, especially Mathematica, for solving problems that are not numerical in nature. So as an example, you're all familiar with factorial. N factorial is n times n minus 1 times n minus 2 down to 1. And double factorial is n times n minus 2 times n minus 4 down to 1 and so forth. And if you were asked to perform the sum of 1 over n double factorial for all values, positive, non-negative values, integer values of n, here's what you would have to do with a hand solution. This took me about 2 hours to do this by hand. It looks all beautifully typeset in LaTeX, but this was all done by hand. But notice at the very end, the answer is the square root of e at the lower right plus the square root of pi e over 2 times the error function of 1 over the square root of 2. Well, that was a lot of work. But of course, using Mathematica, we can do these kinds of problems computationally. So here, you just put in the equation or the term, the 1 over n factorial, and it gives you your answer immediately. You can see it's not simplified, so you do simplification. And if you want to get a numerical value, you of course can do that at the end, do n of this. Incidentally, you'll notice that 1 over n factorial summed like this is going to be e. Now, the reason I put this out is that no numerical simulation will give you that the answer involves the square root of e or the square root of e times pi over 2 or anything like this. This is fundamentally a symbolic problem. And that's what the course is all about, how to use Mathematica or symbol manipulation programs for solving such problems. Here's another one, just an integral. That's what you would learn in high school or maybe first year calculus at college. But here, using Mathematica, you just simply perform the integral. And here's it in traditional form so that we can see it in a easily legible form. Let me give you some more examples of symbolic problems that are very hard. This is from the Putnam exam. Many of you know the Putnam exam is this very elite mathematics exam offered nationwide once a year. And here is that summation with lots of terms, a double summation and so forth. And here, this is what they expect someone to be able to do, an elite mathematician student, to be able to do in perhaps 45 minutes. I will confess it took me about 3 hours to do this by hand, made a lot of errors along the way, but it turns out the answer at the very bottom is 1. Part of my course is on figuring out how to do those kinds of problems using the power of Mathematica or symbol manipulation programs. And I won't go through all the steps here on how you use inverse Mellin transforms and so forth in order to get the answer. But trust me, here it is. Computationally, the answer at the bottom is 1. And I bring this example in to show that it's not just mindless button pushing. It's not just knowing how to do an integral. You have to use your mathematics, your mathematical knowledge, but exploit the power of a symbol manipulation program like Mathematica. So my course is CME, or Symbolic Systems 294, Computational Symbolic Mathematics. And it's the use of symbol manipulation programs, in practice it's Mathematica, to solve mathematical problems that are at least in part symbolic rather than entirely numerical. That is to say, where numerical solutions simply will not suffice. And I break the course up into roughly 40% are basic functions. First of all, I don't assume any of the students know Mathematica at the beginning, and only a small percentage do. I will say by the end of the course, they love those software and they use it more and more regularly. But 40% is on basic functions, how to use integrate or differentiate or solve or limits and things like this. But I think the real value of the course is going a step beyond tricks like using options and assumptions, and how do you verify a solution? If I put in a symbolic solution, integrate this function, and I come up with a solution, how do I know it's right? Well, I will give you some slides in a few moments telling you some of the tricks that I teach. And this is really sort of the heart of the course. It's something that you don't really get from the Wolfram documentation on integrate. It doesn't really tell you, it might give 1 or 2 examples once in a while, but if you integrate a function, how do you know it's correct? Or you do a Fourier transform, how do you know it's correct? Then I spent about 20% on symbolic algebra programming. That is to say, writing functions that deal with symbolic functions, like writing your own derivative function, for instance. And unfortunately, in my class, I only have about 10% of the time where I can go into the fundamental algorithms employed by symbol manipulation programs like Mathematica for doing integrals or simplifying and so forth. It gives them a taste of that. I hope to offer a full course on that in the coming years. And so most of my students are juniors, seniors, and first-year graduate students where they already have a lot of applied mathematics. They know algebra and calculus and differential equations. And often there are a few who lack 1 or 2 of these things like analysis, but nevertheless, they can actually learn some of the content by taking my course. So there are, of course, a number of computer algebra systems, and I think those of us here are all favoring Mathematica for a number of reasons. But for symbolic mathematics, it wins most of the bake-off competitions with other computer algebra systems for symbolic mathematics. And that's why I use it. And I'm a very deep and long-term user of mathematics, and I love it very, very much. So it's better than SIMPy and MathCAD and so forth. what I like to do, and one of the benefits of Mathematica is that it takes what I'll call computer science versions of equations, like here's my term, I define my term, and then you can see it in standard form. So I want the students to think mathematically, even though the manipulation is being done computationally. I want to render problems, terms, equations, and so forth as mathematically as possible. And that's one of the best things I like about Mathematica, is that you can use an integral sign with a lower limit of 0 and an upper limit of 2 pi and cosine x squared and things like that. So it's very easy to think mathematically because you're seeing it mathematically. It also helps you when you're copying equations from a textbook into your manipulation program, symbol manipulation program. You can see that it matches. By the way, I should also point out that my lectures are all on slides just like these. In fact, these slides I just picked and chose from my class. And students compute during class. So I say, they all have this on their laptops, and during class they hit, shift return and do the computations, but then I'll go in and say, oh, let's change this exponent from 2 to 3, or let's add this term, or let's take a higher order derivative, and so forth. So they're computing along during class, and they can also type in their own notes. Remember that the inverse function does this, that, and the other, and so forth. And then they, of course, keep their Mathematica notebooks as their record from the class. And here some of the kinds of non-obvious problems, like the cylindrical decomposition. In other words, if I want to do an integral over this circular region, the cylindrical decomposition of x squared plus y squared being less than 1 breaks that into terms that involve just one variable, like x. X is between -1 and 1. And then y is between minus the square root of 1 and so forth. And so this is the kind of symbol manipulation. This even works if you have, instead of 1, you have x squared plus y squared is less than a, or something like that. And the same thing happens in 3 dimensions and more complicated surfaces and so forth. We talk about integrals over symbolic regions. So integrate 1 over the 2-dimensional disk, and that's going to be pi. Also putting in here assumptions a and b and c are greater than 0, and now integrate this function over an ellipsoid with principal axes a, b, and c, which I have forced to be positive, and it gives you this kind of symbol. Again, note that this is entirely symbolic, not numerical. You couldn't have gotten this answer numerically. I like being able to manipulate equations. So let's define an equation. X squared plus y squared is equal to z squared. Now let's apply sides. This is now the kinds of mathematical steps that you do in calculus and differential equations and so forth. So you use your mathematical knowledge and say, I need to take the square root of both sides. And there you get something like this. And you simplify it, and you get this back, and you're looking at this square root of z squared being unsimplified. Well, if you impose the assumption that z is positive and then simplify, then of course Mathematica will take that square root of z squared and give you z and so forth. You can do this for lots and lots of different types of equations. When I talk to mathematicians, they say, oh, but you're just using the computer, the students don't gain insights and so forth. So I love to show them this little problem and say, all right, would you ever have your students try and solve this symbolic problem? Not numerical, symbolic, where A, B, C, and D, and E, and so forth are real numbers. Well, they say, well, it's good for them to try it. Well, no. This integral The output of this integral is 37 megabytes. True, this is not your typical involving the elliptic function of arc sine and so forth. Look at this. This is really the simplified version of this integral. You could work 10 years on trying to solve this integral by hand, and you would probably make 1,000 mistakes of signs and squares and so forth. So this kind of course allows you to gain intuition about these kinds of problems. And one of the main lessons is that computer algebra allows the scientists and engineers and even mathematicians to focus on the math ideas rather than calculation. It allows you to try out different techniques and so forth. And here is what I mean by symbolic programming. So if you remember from calculus, you can define, or one definition of the derivative is f of x plus epsilon minus f of x over a epsilon, and you let epsilon go to 0. Well, you can actually program that. My d, my derivative of f a function and v a variable is exactly this. Here I do it, and now I can take my derivative of sine of x cubed and cosine x squared and so forth, and it does this. This is a kind of programming you don't do in Python, you don't do in C++ and so forth. But again, how you use your mathematical knowledge to solve problems. And I love this problem, which came from a Putnam exam. This integral from 2 to 4 of this square root of log and so forth. And here it is, defined integral, and let's try it in Mathematica. And when you try it, it doesn't solve it. It can't solve it in this form. Well, just as on the Putnam exam, the trick is looking at this problem, using your mathematical knowledge to say, maybe the limits of integration should go, maybe I should center my variable at x equals 3 and basically do a change in variables. And so you use your mathematical knowledge and say, all right, to use integrate change variables of the integral. I'm going to have a new variable y, where y is x minus 3. And there it is. And now that's my new integral. But you notice it has more symmetry and so forth. And now when you activate it, it comes out the integral to be 1. And so this is really what I spend most of my time, or another way of saying it, it's the greatest value of my course, is coming across these kinds of problems where you use your mathematical knowledge, but you don't spend an hour testing it out. You do it using symbol manipulation. Another class of problems that are very easily done is finding ranges of variables that satisfy a condition. For what values of a is x cubed minus 3x squared plus 3x squared plus 2 non-decreasing? Well, we learn about this. So here is, I also like to have, graphics and manipulates inside class things to give them ideas. So it's clear when a is way up here, it has a decreasing part, and likewise over here. But there's some range of a in which it's monotonic. Well, use resolve for all values of x, the derivative of that function is greater than 0. And there it is. It says when a is between 0 and 1 inclusive. And you can test that out here. Put an a that's greater than 1, and a less, and so forth. So the students do this all in class. They can take this software home, alter it, and then I'll have a homework problem that involves using some of the software that we've used in class, and so forth. So another aspect of symbol manipulation is the domain of the variables. Are they integers, positive integers, negative integers, complex variables, and so forth? So solving this equation over positive integers, you get x equals 369 and so forth. Things like this, or solve 2 to the x equals x over the real numbers and over the complexes. So if you do 2 to the x over x equals this, there's no real number for which that is the case, can be solved, but you do it over the complex, and x is a product log and so forth. You can even get the numerical value. So that's what I do in my course. Also options, putting in options and assumptions, which is one step beyond the kind of thing you'll get in Wolfram Alpha. Many of the students have had access to Wolfram Alpha and used it, but it's really the options and the sort of deeper level of how to use these things in a sophisticated way. Things like counting the roots. How many roots are there of that cubic equation between -2 and 4? Oh, well, there are 2. It even works in complex variables. Count the number of roots of this x to the 12th minus 1, which are going to be these red points in the complex domain, and so forth. Or testing inequalities without explicitly computing the values of each. So you here, the question is, which is larger, the integral over a circle, or a disk rather, or a square having the same area of a dying Gaussian, e to the minus x squared minus y squared? Well, you can put in a particular area and then do this integration, and it comes out to be true that the one over the disk turns out to be larger, even without having to get the numerical value explicitly. We spent a lot of time on statistics and symbolic statistics. So what's the probability that x is less than a if x is distributed normally with some mean mu and standard deviation sigma, and it will give you the error function, as you likely know. And similarly, what's the probability b is less than a given, assuming b is less than a, what's the probability that x is greater than b given that x is less than a, etc. All these kinds of things. So it's a little more sophisticated than you typically do on Wolfram Alpha, and changing conditions. One technique, which I drum home probably too often, is how to test your solutions. So, for instance, if you take a symbolic Fourier transform, you can do the inverse Fourier transform to check whether you're right. So, what's the Fourier transform of cosine omega naught x? Well, that's delta, sum of 2 Dirac deltas, and now we do the inverse Fourier transform of that, and we better come back to cosine omega naught x, and in fact we do. So I do this with derivatives and integrals and a whole host of problems where there's a forward and a backward, a function and an inverse function. Things like continued fractions. Here's what's the continued fraction representation of 71 over 93. And now let's check that that's correct by going from continued fraction. From that solution, let's make sure we go back and get the correct answer. And even for a function like the hyperbolic cotangent of 1, you can go backwards and it will give you, in fact, the correct solutions. One of the more interesting topics I go on to is Grosvenor bases. If you're familiar with row decomposition for linear, in linear algebra, Grosvenor bases, I don't have time to go through it now, is the same with same idea for polynomials. If I have x squared plus y minus z equals -5 and so forth, give me a new set of equivalent equations in which the first one is dependent only on one variable, like x, and the next one by x and y. So here, give me the Grosvenor basis for x cubed minus 2y squared plus 7 equals 0 and xy squared minus 9 equals 0. Well, here they are. The first equation or term depends only on y, which makes it easier to solve. And then once you have the solution for y, you can put it into this one for x. And the one reason I talk about Grosvenor bases is because this fundamental operation is used in some of the deep internal algorithms from Mathematica. And I end with some of the algorithms for performing integrals. I don't have time to go through EDGE, the educated guess algorithm, but if you have a function of the general form f of x, sine of g of x, you have a general form for the output, and the goal is to find these polynomials. Again, I don't have time to go through it, but this is really the innards that you won't get in a mathematics course, but you do get in something that's dealing with computer algebra. And so in summary, there are a wide range of symbolic mathematical calculations that are now automated, and Mathematica and my course allows the users to think more like a mathematician and not have to worry so much about the calculations. I do think the students at the end of the day are real power users. If you think of, I like to advertise my course as Wolfram Alpha on steroids, that you now have much, much greater control than you have over Wolfram Alpha and so forth. So the kind of problems you can do are more complex. There are also new programming style, being able to define your own derivatives or other functions or even integrals, or writing programs to do the substitution of variables in an integral, or break an integral into different portions and so forth. And many of these techniques enhance the power of students in solving problems. So that's computational symbolic mathematics. I'm writing a Wolfram book on the subject. Maybe if you're interested, if you teach your own courses, get in touch with me, and maybe I'd be able to share it. Anyway, well, thank you very much for your attention. I do have time for questions. Put them in the Q&A or chat, whichever you like. Do I have to hit the Q&A? Oh, here we go. Although your emphasis in particular was focused on mathematics, doesn't your overall message apply equally well to a number of topic areas? Information theoretic, as they become approachable. Yes, I think though, but by focusing on mathematics, that's the foundation. You use your mathematics then in your course on information theory and so forth. So I do take examples from different domains and different engineering domains. And in my first class, I asked students to contribute problems that they'd like me to solve. And so I'll get some from fluid dynamics, and some from information theory, and some from machine learning, and so forth. Next question. I noticed in your symbolic algebra program, you use mydfx instead of the most usual mydfx. Oh, there should be a colon equal. My mistake, sorry. Thank you for catching that. Was it difficult to convince colleagues at Stanford that such a course is needed useful? What was the winning argument? This is an extremely good question. This is an extremely good question because I went to them. And it did take a bit of convincing. And I just took 3 or 4 books from fields that I know the students will be using, and I would turn to this page and show a symbolic problem. And how do you expect your students to solve this problem? And they look at that and they say, oh, gosh, I don't know. And I say, I can teach you how. So yes, this was the first course. And as far as I know, this is the first course in the country. Maybe someone else has done something similar. But I must say Stanford, once they had it, and they said, oh, we'll test it 1 year. Now I'm teaching in my 3rd or 4th year by now. The students love it. The class is growing slowly, and so forth. Ideally, much of what's covered in this course ought to be integral to courses in calculus, differential equations, linear algebra. Why isn't it? In some sense, it is, but it's not done enough. So much of calculus, especially when I took calculus at MIT and so forth, they are the solution technique. So, trigonometric substitution and all the different techniques. and you spend a lot of your time doing that rather than thinking on math. Oh, I see my time is gone. I don't know if people can hear me. I will answer one more question. One of the most complaints I've heard over a long life is that so many math teachers cannot explain the practical utility of their topic. Is Mathematica particularly helpful in this? Yes, I mean, you're solving problems that you couldn't have solved otherwise. So I believe my time is up. I can't tell if you're still hearing me, but if not, you have my email. Feel free to ask me questions after when you think on this. It's not possible to audit the course online. I'm sorry. So I guess we're over here. Thank you very much for coming.